Hello, hi. My name is Khaizuran bin TUAH and my ID number is FB19014. So I will be introduced for the assignment topic. Okay. A PID controller is a continuously calculate an error value A instead of T as the difference between a desired set point and a measure process variable and applies a correction based on proportional, integral and derivative terms. PID is an initialism for proportional integral derivative, referring to the three terms operating on the error signal to produce a control system. The ball and the beam system are also called balancing on a ball on the beam. It can usually be found in most university control labs since it is relatively easy to build, model and control theoretically. The system includes a ball, a beam, and a motor, and a several sensors. It is generally linked to real control problems, such as horizontally stabilizing an airplane during landing and its turbulent airflow. There are two degrees of freedom in this system. One is the ball rolling up the the beam, and the other is the beam rotating to the one's end. Ball and beam system is a very interesting system by its non-linear dynamic and is under actuate phenomenon. This type of system have a wide range of industrial application including passenger platform, balancing for comfort in luxury car, control of exothermic chemical process where addition of heat accelerate the process, control of rocket and aircraft vertical takeoff and liquid carrying a tanker on the road where liquid behave like a ball on a beam. Together with interesting application, its dynamic give a wide range flexibility to implement a classical, modern and advanced control system theory. The aim of the system is to control the position of the ball to a desired reference point and reject disturbance such as a push from a finger. The control signal can be derived by feeding back the position information of the ball. The control voltage signal goes to the DC motor via a power amplifier and then the torque generated from the motor drive the beam to rotate to the desired angle. Thus, the ball can be rotated at the desired position. It is important to the point and that the open loop of the system is unstable and non-linear. The problem of instability can be overcome by closing the open loop with a feedback controller.
Assalamualaikum warahmatullahi wabarakatuh. My name is MUHMMAD SHAHIR bin ROSLI and my matrix number is FA18021. So my part in this project is methodology. I will start with open loop root locus. So the main idea of the root locus design is to estimate the close-up response from the open loop root locus plot by adding zeros and poles to the original system. The root locus and thus the closed loop response will be modified. Let us first view the root locus for the plan in open loop. Create a new M file with the following MATLAB code in order to model the plan and plot the root locus. Now, run the M file and you should see the following root locus. As we can see, this is my root locus. The system has two poles at the origin which go off to infinity along the imaginary axis. The design criteria can also be plotted onto the root locus using the sgrid command. This command generates a grid of constant damping ratio and natural frequency. The damping ratio and natural frequency were found using the following equation which relate them to our maximum percent overshot and setting time requirement. The equation with T is found by assuming the system has settled when the response remains within 2% its final value. From this equation, the damping ratio and natural frequency were found to be 0.7 and 1.9 respectively. So this is my root locus. The area between the two diagonal lines represent location where the percent overshot is less than 5%. The area outside the curved line represent location where the settling time is less than 3 seconds. Note that no region of the plot falls within the design criteria shown by this line. To remedy this and bring the root locus into the left-hand plane for stability, we will try adding a lead compensator to the system. Okay, next, lead controller. Lead compensator leads to shift the root locus into the left-hand plane. More detailed description of lead compensator refer to LED and LED compensator design page. A LED compensator has the form given below, which is C as equal to KC, where the magnitude of Z0 is less than the magnitude of P0. Now, add the controller to the plan and view the root locus. We can find position the 0 near the origin to cancel out one of the poles. The pole of our compensator will be placed to the left of the origin to the pull root locus further into the left hand plane. Add the following lines MATLAB code to your M file. Next, run your M file in the MATLAB command window and you should see the equation. Okay, this is my root locus. The branch of the root locus are within the design criteria. Okay, next, selecting the gain. Now we have to move the root locus into the left hand plane. We may select a gain that will satisfy our design requirement. We can use the rlogfind command to help us to do this. Add the call into the end of M file. Then go to the plot and select a point near those indicated by the cross mark on the pilot on the plot below. On the plot. Okay, now this is a root locus. After this, we can follow output in the MATLAB command window. The value written into MATLAB command window may not be exactly the same. Should at least have the same order to magnitude. Now the response within this gain. Okay, now plotting the closed loop response. This value of k can be put into the system and the closed loop response to a step input of 0.25 meter can be obtained. And the following line to M file to perform this analysis. Next, run M file and select a point on the root locus similar to the selected point above. The step response should look like in this window. Okay, this is step response. Okay, from this plot, as we can see that when 0.25 meter step input is given to the system, both the settling time and percent overshot design criteria are met. A design problem does not necessarily have a unique answer. Using this method may result in many different compensators. Try running M5 several more times, selecting a different point each time, and study the effect this has on the step response. For practice, you want to go back to the original open root locus and try to find other ways to add zeros and poles to get a better response. Okay, that's all from me. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Anwar Shadi bin Kamar Zaman, and I will explain about methodology, which is part 2 about the Simulink controller design in the Simulink. Okay, first, to build a model, create a blank window, and after that, insert an integrated block from the continuous library and connect each other and label it as D over dt R. After that, insert an output one block from the sync library and connect to the first integrator and label as R. Single click on it to change the label as R. Insert a FNC block from user-defined function library and connect to second integrator. Label the FNC block as ball beam Lagrangian model. So put this formula with the value of the expression part, and then this expression part, and then close dialog box. Insert the mark block from the signal routing block and connect the ball beam block. Change the number of input to 4 for the mark block. Connect the mark block for first input to the line of the R signal. Meanwhile, the second input is connected to the line of D over dt R signal. Insert an input one block and a gain block from commonly used block library and connect each other. Next, label block input one as data and edit the gain value to D over L. Connect the output of the gain block to third input of the mark block and label as alpha. Underneath the alpha line signal, insert a derivative block from continuous library and connect the output of the gain block to input of the derivative block. Then connect the output of the derivative to the fourth input of the mark block. The model is, and then save the model as ballbeam.slx. So it will become like this. So the next part is open loop model. First, create a new blank model window, and then insert a subsystem block is from port and subsystem library and open subsystem, and then open the ballbeam.slx and click CTRL-A and CTRL-C, then CTRL-V into the subsystem window. Close the subsystem, then untitled window with the input label data and output label R will appear. Label the subsystem block as ball and beam model by single click on it. Insert a step block from the source library and change the step time value to 0. Okay, next, close dialog box and close the dialog box of the step block. Insert a scope block from the sync library and connect all blocks. Lastly, save as open loop tf.slx. So it will become like this. And then we need to run the simulation to obtain the step response. After that, to open the scope block, double click on it and the response will appear. Okay, next is the last part is for building lead compositor, which is closed loop model. Okay, via open loop tf.slx, the line between ball and beam block is eliminated. Then place a transfer function block from the continuous library and link the ball and beam block. The block label lead compositor is the transfer function. The numerator has been adjusted to 1 and 0.01, and the dominator to 1 and 5. Insert the game block and attach it to the lead compositor input. It has been updated to 37.1. And then insert the link of sum block to the gain block input. The value has been replaced with plus and minus. So the output of the ball and the beam model is linked to the negative input of the sum block, while the positive input of the sum block is connected to the step block, and then save this file as a closed loop tf.slx. Through a double click on the scope block, the answer will show. Okay, I think that's all from me. Thank you.
Okay, Assalamualaikum and good day. My name is Daniel HAZIQ, RIZAL FP18125. I'm about to present the result for our project. So this is the MATLAB representation and open loop response. The first one is transfer function. The transfer function found from the Laplace transform can be implemented in MATLAB by inputting the numerator and denominator as vectors. To do this, we must create an M file and copy the following text into it, which is M equal to 0.111, R equal to 0.015, G equal to negative 9.8, L equals to 1.0, D equals to 0.03, and J equals to 9.99 exponent negative 6. And then K equals to M times G times D divided by L times J divided by R 2 plus M. Then okay. And then num equal to K then equal to 100 basis num then. And then our output should be num divided by then, which is 0.21 S2 divided to S2. Now we would like to observe the pulse response to a step input of 0.25 M. To do this, we will need to add the following line to my M file. Okay, satu, dua, tiga. Now we would like to observe the pulse response to a step input of 0.25 M. To do this, we will need to add the following line to our M file. So this is the line, and then we will get this output. From this plot, it is clear that the system is unstable in open loop, causing the ball to roll right off the end of the beam. Therefore, some method of controlling the ball's position in this system is required. 3 examples of controller design are listed below for the transfer function problem, as may select from PID, root locus, and frequency response. Okay, next I will pass to Muhammad FAIZ.
Assalamualaikum. My name is Muhammad FAIZ bin ZULKURNAIN with metric number FB18041. And for my part, I will show the result in the state space, which is the linearized system equation, which can also be represented in state space form. Well, this can be done by selecting the ball's position and velocity as the state variable and the k angle as the input. And the state space representation is shown in the form of matrices formula. However, for our state space example, we will be using a slightly different model. The same equation for the ball still applies, but instead of controlling the position through the k angle theta, we will control the alpha double dot. And this is essentially controlling the torque of the beam, which can be represented in the new form, which also in the matrices form. But for the system, the gear and the lever arm will not be used. Instead, a motor at the center of the beam will apply the torque to the beam, which to control the ball's position. Okay, for the state space, the equation can be represented in MATLAB with the following commands, which this equation are for the torque control model, which is M equal to 0.111, and for the R, for the capital R, which is equal to 0.015, and the G negative 9.8, and J 9.99, exponential negative 6, and for the H, which is the formula is negative M times by G over J over R to the power of 2 plus M. And this is the following matrices for A, B, and C, and D. And the step response to a 0.25 meter desired position can be viewed by running the command below, which is step bracket A, B times 0.25 C, D. And our group output should look like this graph, which is like this. And for the plot for the transfer function, this plot shows that the system is unstable and the ball will roll right off the end of the beam. Therefore, we will require some method of controlling the ball's position in this system. And the state space example below shows how to implement a controller for this type of system. That's all for our part. Thank you.
My name is Muhammad ROHELAN. My entry ID number is FB18022. Next, I will present the discussion of the project. In this project, root locus control strategy was designed and applied on ball and beam system for stability and ball position tracking control. The design is based on the following design criteria, with each overshoot of 5% and settling time of 3 seconds. The system is type 2, which means that it has double posts at the origin. Thus, the open loop system is highly unstable and nonlinear. When the voltage is applied to the open loop system, the ball will roll right off the beam end. Based on the results obtained, the design criteria was satisfied. Modern control systems are often complex and require some sophisticated performance criteria, and so error and time are the important factors that must be considered. As a conclusion, root locus control system has the most stable system, and it is have 5% overshoot and can reach the settling time to reach 3 seconds. Therefore, it is ideal to use root locus control system for a theory method where no noise parameters that will be involved in obtaining the best result for the output. Thank you.